All right, so the first topic of this course is transformers. All right, now we're going to go into what it is, how they work, but frankly, how they work is less important to us than the function, right? How we can use them to work. Because how they work gets into like all this physics stuff, which sure, interesting, but as an electrician, as anyone focused on trying to maintain things operating, the what's going on in the electrons of a transformer is not so important to us. All right, but let's get into the first bit about it. Now, this is all posted along within the PDF. So I'm going into the first page of the PDF. Except, like I said, I'd rather cut out a few things here and there. So this is the whole PDF. What I have on the whiteboard is sometimes only a couple of things out of the PDF, but we'll work with both. All right. So I'll have the PDF along with me. All right. So what is an electrical transformer? Now, this is pretty old. I had to look it up. I thought it was older than the light bulb, but it is not. It is only not older or as old as the light bulb. I think the light bulb like a few years older than the transformer. So a transformer is a static device. All right. So what does it mean by static device? It means it is a simple component. It's got no moving parts. There's nothing in a transformer that's doing any kind of movement, all right? One of the good things about transformers, as we focus as a maintenance electrician or industrial electrician focused on fixing machinery, is they don't go out that bad. They don't break as much. There's no moving parts. Your motors go out. Things that are moving, conveyors, belts, chains, they break. Transformers, no moving parts. They don't break as much, if at all. Now, purpose of the transformer. Transfers electrical energy from one circuit to another through electromagnetic induction, and that's where the physics is taking place. All right, so I'll explain a little bit about the physics as we go through this. Now, electrical energy, I want to kind of make that a little bit more geared towards an electrician, which is in the next sentence. This is more about voltage. Because when you say energy, energy is actually watts or wattage. That's energy. Energy is measured in two ways in the US, everywhere else in the world, or almost everywhere else in the world, only one way, which is wattage or kilowatts. That's what the whole world does, wattage or kilowatts. The US, we do one more. Does anybody know what the other unit of measuring energy is in the US? Horsepower, yeah. The other one. We're the only ones. Motors in Europe are kilowatt or watt size motors. Right, there's actually a way to figure out, if you have a European motor and you got to buy a American motor now to replace it, then there's a conversion. But basically, transfer it over to wattage and do some Ohm's law. But when we're talking about transferring, right, when it's using this word transferring electrical energy from one circuit to the other, it's actually the voltage that's transferring from one side to the other. In the next sentence, it is primarily used to up or down, increase or decrease voltage, all kinds of different levels while maintaining the same frequency. I guess not as important, but just to explain that, it means that 60 hertz on both sides. Voltage is going to go from a high voltage to a low voltage from one side to the other side of the transformer. We'll get into primary, secondary, input and output, both the same. But the hertz stay the same. All right? There's no way to change the hertz unless you have a couple of other ways to change it, but a frequency drive would be. And then the last part is just on the transferring of the energy, the transferring of the voltage from one side to the other. Because these things are not perfect, there is some loss. So transformers are typically 80 to 95% efficient. These will be like larger transformers lose more energy. Smaller transformers, like maybe 12 volts stepping down to 5 volts, something very small, then less of an energy loss just because there isn't a lot of energy being transferred. The more energy you're transferring from one side to the other, the greater your energy loss is going to be. That has a couple of effects. It affects the voltage and the wattage a little bit on the primary and the secondary, but it really doesn't have much of a worry for us as far as understanding how transformers work. So there's the first bit about it. All right, what does it do? Is it changes voltage from one side to the other. Now, how does it do it? Well, I'll explain a little bit. Like I said, this is the lesser important part. But inside of a transformer, let's see. Well, we'll get there in a second. We have two sides of a transformer. So we'll design a little block like that. It's kind of just for the illustration part. So it all has to do with this right here, and that is a winding. All right, they take one wire and they wind it around one piece of metal on one side of the transformer. Now, when you run voltage through something wound up like that or coiled up like that, sometimes this is called a coil as well, or a winding, both the same. Sometimes a coil, like for example in motor control starters or relays, and then in motors they're called windings, but it's the same. It's one wire that turns many, many, many times, sometimes 2,000 turns around a piece of metal. And when you make such a tight winding like that, when you apply voltage, doesn't matter what voltage you apply. For example, you can put a hot and a neutral on one side of the transformer. So for example, this would be a 120 volt transformer where the input is coming into the transformer with 120. What happens now is as you apply this voltage, you create a very, very, very strong electromagnetic field on the side that you applied the electricity to. All right. That electromagnetic field then gets picked up by the piece of metal. So once you energize this winding on this side and you create the magnetic field, now the entire piece of metal that this thing is wrapped around picks up this magnetic field. And now all you have to do to build this transformer, very simple, is put another coil on this side. And now, if you want more voltage, then you need more windings or more turns on this side. For example, 3,000 on this side. If you're trying to reduce the voltage, then you would simply have less windings on this side. This would reduce the voltage. All right, now we'll get into a lot of the terminologies on primary, secondary, and we'll get to a little bit more. But just in a bigger picture, this is how a transformer is working. All right, one side is energized. That side creates the magnetic field. That magnetic field, because it is connected to a piece of metal, gets picked up, and that is what the induction part is of the electromagnetic induction. Induction is the piece of metal picked up the magnetic field. It happens a lot in electrical. It happens if you bring a wire next to another wire that has amperage on it or current running through the wire. That wire will pick up the magnetic field of the other one. All right, so a piece of metal close to a magnetic field can pick up that magnetic field as well. This is why a lot of times, not fiber optics, but data communication wires like phone wires and things like that, they have to stay away from our electrical wires because our electrical wires are producing electromagnetic fields around them. And if some sort of other data communication comes near it, they're going to pick up that magnetic field, and then they can have, bad. Well, these days you don't have cable anymore, and you don't have phone lines anymore in the house. But you used to have scrambled phone lines. You couldn't hear something too well. It was usually some magnetic field interruption or EMF, electromagnetic interference. So understand that. As soon as you apply electricity to the winding, magnetic field is created, and then we transfer it over to the other side. All right, not so simple, but pretty much that simple. All right, any questions for that? So far, so good. Pretty straightforward. All right, if we look at the next note, then it gets into, again, some physics. Faraday's laws of electromagnetic induction. A transformer operates based on Faraday's laws of electromagnetic induction, which state that a changing magnetic field, and why is our magnetic field changing? Because, and actually one thing I didn't point out in the beginning, which is AC voltage. All right, I did not make mention of that. Something very important for you to understand. Transformers only work on AC voltage. It's the alternating current that creates that magnetic field. So going back over to the note, and there's where I was, that's why it says changing magnetic field. It's actually changing, it's actually going in and out. It's dropping, it's intensifying, or it's reducing and it's intensifying. Reducing, it's intensifying as we go from positive to negative. But again, that's more of the physics side of things. So we have a changing magnetic field, again, induces a voltage on anything nearby. That's metal. Obviously, if it's plastic, it can't pick up the magnetic field. But anything that's metal can pick up the magnetic field around a wire. All right, I remember one time I was building a Kmart, and there was a parking lot, and we had a light pole that we had to install with lights on it. This light pole happened to be, whoever designed the blueprints didn't know this, near some electrical wires passing by. And it was so close to the electrical wires that the magnetic field around the electrical wires potentially were close enough through induction to be able to be picked up by the light pole. And now literally the light pole is energized. So somebody could touch that, and of course, bad things happen there. So any piece of metal that's near, like power lines and stuff like that, metal is picking up that magnetic field. All right, so the changing magnetic field induces, shoots a voltage over to anything nearby. Again, the transformer is built in a way to take advantage of that. In fact, let's start with the middle one, the core, the inside part. All right, a magnetic core that helps transfer energy between the windings. All right, and so the way they built the transformer, now just take a look at this little one. This is a small transformer. It's 230 volts on one side, and the secondary side is coming out as 12 volts. Again, 12 volts AC, but we do not need to write that because it cannot be DC. It happens to be that this one comes from Europe, I believe, because that says 50 hertz. Although, could be still used in the US, it'll be fine. So the way this transformer is built is you have one winding around one side, you have one set of wires around the other side, and this is each end of that single wire coming out on one side of the transformer and the other side of the transformer. All right, so let's get some names now. I'll leave the 230, but we don't really need the voltage just yet. So, primary side and secondary side of the transformer. All right, the primary side of the transformer is the input side of the transformer. All right, we know the primary side because that will always be, and this isn't about voltage right now, but it'll always be on the side that has the voltage source, wherever we're getting power from. We'll talk about that, where we get power from. In fact, I'll go to the code book just to point out a few things from it. So the primary side of the transformer is the side that's connected to power, connected to the voltage source. All right, if you were looking at, let's say, for example, a doorbell transformer. They don't have these anymore. These things are starting to phase out of residential. They're still around, the old school doorbell where you pressed and it made a sound inside the house, not the Nest, or not the Nest, but whatever the one that's connected to an app now.
Ring.
There we go, Ring, and all these other ones. Now those are just there. There's a battery inside. You just stick it to the wall with some glue. Really, it's becoming very easy to be an electrician now. But the old school ones, back in my day, or even still in older homes, they had one of these. They had a transformer. And they would connect 120 volts, and the doorbell would work off of 12 volts. And so you would have to find somewhere to plug this in, right? Just pick up 120 somewhere in the house. So that becomes the primary side. Again, the side that's connected to the power source, or as it's written here, voltage source.
One cable would be hot and the other cable would be the neutral? Or?
Yes. We'll talk about those because different voltages. This one is 230 volts. So this one's a little bit different. All right. In this one, then one side would be hot and the other side would be hot as well. In the 121, let's go over to 120. Then one side would be hot and one side would be neutral. Technically, it doesn't matter which side, although we try to keep some order in the world of, so I'll talk connections in a little bit when we get to those. But either one doesn't matter now. So
and then the other side is still hot and neutral?
Exactly, very good. Because we're still dealing with AC voltage, we're not positive, negative, DC. One of these also, yes, hot, and the other one will be neutral as well.
Even though it's the bigger one, the 230?
Yeah. Even if this was 230 over here where we had hot, that is the design of this transformer to input or primary side connect to 240 volts, 230, 220. This 230 is actually an engineering way of breaking down, and this is something regional. If you work in different areas of this country, you'll find out that some states have 220 and some states have 240. California has 240, New York has 240, but Florida is 220. I grew up with 220. So for me, it wasn't 240 outlets, it was 220. For me, the outlets on the wall aren't 120, they're 110 when I was coming up as an electrician. So manufacturers just put 230 as the middle ground between both of those. So I'm just saying, don't get confused by that 230 as something odd. So yes, on the other side, then you would get 12. You would get 12. And there's a way to build the transformer to get that. Good questions both. Now, the other side's called secondary, and this would be the output side. And this is the side that's going to connect to, as it says here, delivers the transformer voltage to the output circuit. All right. Another way I like to explain that is to the load, to whatever is going to use the electricity. In the case of the doorbell, it's the doorbell. In the case of the transformer that's feeding the electricity to your house, then your house is on the secondary side of the utility company's transformer.
And those two hots, are they from the same circuit? Yeah, right? They're from the same wire.
So, yeah, these two hots over here?
Yeah. Like
okay, cool.
If I'm going to connect it, I just grab the other hot?
Yes. So the way we would connect this one, let's say, for example, we'd find a panel.
Yeah.
And we'd need a 2-pole breaker. All right, this breaker would be what we call a 2-pole breaker. A 2-pole breaker provides both phases. It provides A phase and B phase, and then we would run one to one and one to the other. And so you'd flip this breaker on, and then you energize the transformer. On the secondary side of the transformer, you can measure with your meter or whatever, and then you'd measure 12 volts on that side.
The doorbell needs its own breaker then?
No, the doorbell wouldn't. I'm just explaining the connection to something. But the doorbell would not need its own breaker. You would pick it up from some other circuit. However, let me just explain. This is not a doorbell transformer. Maybe that was the confusion. This one specifically is not a doorbell transformer, only because I've never seen a doorbell transformer require 230 incoming voltage. Usually a doorbell transformer, since it's used in a house, it is going to have 120 on the primary side.
Okay, got it. That's what.
Yeah. There, yeah. This one is probably for like industrial lights or something like that, or maybe a small 12-volt motor inside of a machine or something like that, or for example, inside of a dryer or some kind of industrial machine that requires 230 to the machine, but something inside this machine, some kind of small relay, some kind of small little circuit board, needs 12 volts somewhere in there.
Okay.
All right, good. You'll find this also in appliances. Microwaves will have these little transformers where 120 down to even 5 volts, but just to explain how we'd get 230 from this one. But for right now, voltage is not so much the worry, so we'll talk more on different ways to combine to get different voltages. So just to fall back a little, this is primary side, secondary side. Primary side input voltage, or again, voltage source or power source. It's always the side that we're connecting to where we picked up the voltage, and this is the side connected to the load or to that second circuit.
Okay.
All right, good. Now, going back over to the full PDF, and actually we centered that. It wasn't actually centered. If we read this last sentence, just gives us a little bit of a better breakdown of what's going on. I've already talked about it, but just to reinforce what I said, when AC voltage is applied to the primary side, again, always AC voltage, it creates the changing magnetic field in the core. And so this core, which you can't really see here, but this core connects both of these sides together. All right, this core is built in a way where the windings around this one and the windings around that one are connected by the core. So once the primary side creates the magnetic field, the core technically is picking it up, and the secondary side can take advantage of it. This induces a voltage on the secondary winding, which depends on, well, we'll get to this. The voltage will depend on the turn ratios. All right, if there's anything there that you have a follow-up on. Now, there's a lot of different transformers out there. Like I said, big transformers, little transformers. So the codebook has a little bit to say about it. All right, a little bit to say about it. If you have your codebooks nearby, you really don't need to. There's only a couple of things that I want to point out here. But if you do, and you want to jump over with me to page 373, then you'll be where I'm at, as far as the article that covers transformers in the codebook. They don't have much to say about it because one of the main focuses of the codebook, big difference between the industrial electrician and the journeyman electrician, is the journeyman electricians is focused on this word, installation. Whereas the industrial electrician is likely not installing anything, but taking care of or making sure that things that have been working for sometimes 10 years, 20 years, 30 years continue to operate. So the codebook, again, is just really going to focus on installation of transformers. Now, the one thing I want to point out here is overcurrent protection. Breaker was just mentioned. How do I get power to a transformer? So since we're talking about power sources to the transformer, let's go into that for a second. All right. So the codebook says this about protection, overcurrent protection. First of all, let's break down what overcurrent protection is for my folks that haven't done the code classes, and they have more of a conversation on this through the code classes, but let me slide this over now to the overcurrent protection comes in two forms. Protection. Sometimes it's just simply abbreviated to OCPD, overcurrent protection device. In fact, there's a whole article in the code book on overcurrent protection devices, which is Article 240, if you are interested. An overcurrent protection device, as it's pointing out here, or device, is two types. Sorry, we didn't need the word device there. I meant to put breakers or fuses. All right, this is a breaker or a fuse. All right, if you can't see something I wrote on the board, also let me know. I think sometimes that bottom right can have images. So it's saying this about the selection of breakers and fuses for transformers. Right? When we go now to protect this transformer right here, the one you're staring at on the whiteboard, then it has to comply, shall comply with the below, down here. A, B, and C. A, B, and C. Now, all three are different. We are more concerned with B. Why? Because that's 1,000 volts or less, which is what you'll be working with. Not 1,000 volts or more, right? Higher than that. So we don't worry about that. Now, this is going to kick us down to a table way down here below it. Now, not this table on this page. This is the table for over 1,000 volts. We got some big high percentages here. So if you look at the other table on page 374, again, if you're following me with the code, I have the table here. Then this is what it says for maximum. The largest size rating is what that means, maximum breaker. All right, the biggest breaker or setting that I'm going to use to protect a transformer shall follow one of the bottom ones down here. Now, the primary side, and this is what I wanted you to focus on. Notice the size of the amperages running through these transformers. They are very small. Amperage less than 2 amps for my students who did motor control. Your control circuit transformers. Sorry, I'm just going to head over to this note. Your control circuit transformers have less than 2 amps on them. So sometimes there's small transformers that are operating in systems that are running less than 2 amps through the conductors, through the wires. Very, very little amperage, because they're more so concerned about the voltage. All right, those control circuits, like motor control, lighting, and traffic signal control, they are using low voltage. So they're really worried about getting 12 volts to all their components. A little bit larger lighting systems. Really, this is the lighting system world. A little bit bigger, but less than 9 amps. So whatever you're operating is less than 9 amps. A bunch of lights for warehouses and things of that nature. And now the large ones, really for anything else above 9 amps. You'll notice this is a very odd separation of amperage in the code book. Right, some weird numbers to go with, but it is the transformer world. Now, what is this saying? We really do not so much have to concern ourselves with the math here. In other words, this math is not going to come up in any assignments later on, but I do want to explain it. So this is what it's saying. The voltage that's going to feed this transformer has to be protected by a breaker or a fuse. When you go to select that breaker or that fuse, whatever amperage the circuit is going to have. So let me design it real quick. Here's my transformer. We'll have, let's say for example, 12 volts coming off of this side, and we'll stick to the doorbell just for now since it's something everybody recognizes. And let's say the doorbell, when I press this doorbell, generates very little amperage, let's say 2 amps. All right, every time I press the doorbell, 2 amps of current is now on the wire. As soon as I let it go of the button, then it goes away. So it's there, sometimes it goes away. So here's what it's saying. The breaker or fuse, if you're going to put And again, you have to worry too deep about primary only protection or primary and secondary protection. It does change the numbers here, meaning if you're going to put a fuse, let's say for example, on the hot, on the primary side, you wouldn't put it on the neutral. The neutral does not need a fuse. And you're going to put a little fuse on the secondary side of the transformer. Now you're doing this one. In other words, primary and secondary have protection, right? Primary has, secondary has. This fuse has to be 250% larger than 2 amps. Now, that's not a lot for 2 amps, but it is a little bit bigger than 2 amps, not by a lot. But 2.5 times, that's how we would do that, 2 equals 5. All right, the math would be 2.5, 250 converted. Sorry about that, 250 converted. Times 2 amps equals 5 amps. So this fuse and this fuse need to be 5 amps to protect this circuit. And now any percentage along the way, you just match whatever it is that you're doing. All right, if you're only putting protection on the primary side and you're working or operating with higher than 9 amps, then 125% if you're only putting a fuse on the primary side. And if you're putting a fuse on both, then 250. And so, again, just some quick math. It's not going to come up, but I did want to explain, one, the focus of protecting the voltage going into the transformer. All right, you can protect both, but they really want to make sure we're protecting the voltage going into the transformer. All right, fusing that side of things. Because if anything happens on the high voltage side, you don't want it coming into the low voltage side. Now, it's a good idea to protect on both sides, like I just had, fuse on one side, fuse on the other side of the transformer hot conductor. That way, if anything happens on this side, a short circuit does not find its way in, through, and into my low voltage side. Much less of a concern, but also then we have a fuse protecting from that. But 12 volts short circuit affecting the higher voltage side, not much of a concern. But now you have this fuse to deal with the short circuit, and if anything happens, you also have a secondary fuse as well. So you can have both fuses, but again, they really want the first. This is the most important one, the one on the primary side. That's the high voltage side. That'll be the bigger fuse dealing with anything on that side, protecting it from getting into the low voltage side. There was one other thing that I wanted to point out, but yeah, not so big of a note, but since again, some of you have not done the code classes, this is an extra mention. I'll come back now to where we were at. Going back over to the transformer. But down on page, the one extra note here, down on page 373 of the same article, it just makes mention of the grounding and bonding system in that bottom note right there for grounding and bonding, 45010. The transformers that you're going to be working with, the one you guys see here, this is a dry transformer. Some of them are oil filled to deal with high heat and stuff like that. The ones we use are not, so this is a dry transformer. And it says where separate equipment grounding conductors and supply side bonding jumpers are installed, there is a terminal bar for all grounding and bonding conductors connected. Those of you who did code C should have some idea of what's going on there. But this is what it's saying. What this is saying is this little transformer has to be grounded. All right, it's gotta find a grounding system. You do have to protect the outside metal of the transformer. Now, this little one, it's not such a big deal. I'll provide some more pictures with this one when we get into the large three-phase transformers. But the large transformers, the ones for power distribution in buildings, the grounding system gets very, very, very critical that it's set up correctly. I'll show you more images of that when we get into the three-phase transformers. But transformers also need to be grounded as well. All right. One, they're a piece of metal, and as it says there, anything else that is built around the transformer, all right, shall be bonded to the enclosure. In other words, the ground inside needs to be connected to the metal on the outside of it, all right, in accordance with an article that explains how we ground systems. That's really all I wanted to point out of the code book. Not much else from the code book that we need as far as understanding transformers from our end. All right, but if anyone has any extra questions there, anything to follow up on? All right, if not, we'll move on to the next part. So actually, I'll go back one. All right, we have a primary side of the transformer, and we have a secondary side of the transformer. Remember, the primary side of the transformer is the side that the voltage is connected to, the power coming in, the breaker, the fuse, something providing power to the transformer. Secondary side is the one that connects to the transformer or where the load is. Now, there's two types of transformers out there. One of them is very common, which is the step-up transformer. All right, we'll head over to the types of transformers that there are. The most common is a step-up transformer, one that increases the voltage. Not so common, but also out there, is one that will decrease the voltage, a step-down transformer. And all of these are variations of those. All right, the other four. So let's go one by one.
Is that a step-down transformer?
Say that one more time.
Was that a step-down transformer or step-up?
This one that we have here?
Yeah.
Okay, good question. So I don't 100% know because I don't have the box to this transformer, but a few things that I'll use in my brain. One is, more than likely, it's a step-down transformer. And 230 volts with 12 volts on this side is probably the use for it, meaning I have 230 available and I need to pick up 12 volts. Usually it's not the other way around. Usually it's not I have 12 volts and I need 230, but can you? Yes. Who does it? An RV does it, right? Your car does it as well. Your car, you can buy those little adapters that plug into the, what used to be the phone, used to be for the ashtray or for the cigarette lighter, but not anymore. 12 volts, so you can get 120. So there are a lot of uses out there for step-up transformers connecting to low voltage. Now, your car's a little different. Why is your car a little different? Because it's DC voltage. So your car has to first convert the DC voltage to AC voltage, or the things that you're plugging in. You're first converting the DC to AC, and then you're stepping it up. So they're a little bit different, but in principle.
Okay.
All right, so let's talk about the step-up transformer first. All right, so we'll design a few notes around these. Get this up. And now, this is separate. So a step-up transformer increases the voltage, meaning sorry, I meant to put step down first, but we're doing step up first. Yeah, sorry about that. I thought I had step down first. I have it, I guess, second. This is, it is common. Step up is common, but it's common in worlds where low voltage worlds that are trying to increase voltage. Now, usually this is happening in a small voltage world, like 12 volts to 48 volts. Or 12 volts to, 36 volts, or 5 volts to 12. Something like that. Less common out there would be trying to step up large voltages. Something like 120 trying to step up to 480. These are large voltage changes, not as common. In our electrical world, as far as buildings and residential and things like that. Now, one of the worlds these exist in the most, and in fact, we wouldn't have what we have if these things didn't exist, is in power distribution. A step-up transformer is how the electrical company gets voltage across power lines. There's a transformer, and you probably drive around them. There's one near the school over in Anaheim. It's called a substation, large, fenced-in area. You probably see these large transformers inside, or large units. You're like, what are those? Those are big, giant transformers. Because the voltage that's coming from the power producing station, I have a nuclear power plant here in Chattanooga, Tennessee, is where I'm at. Some places have windmills, some places have the Hoover Dam that's, using water as the power source. That's got to be brought into these substations on really, really, really high voltages. They come in on lower voltages, and then to be able to get them all the way across a city, then I have to step up the voltage into high numbers, like 100,000 volts. But the electrical company is only producing something like 20,000 volts. All right, so their generators only generate 20,000 volts, and then a transformer steps it up to a higher voltage. Now it goes across power lines, long distances. That's why the voltage has to be so high. And then by the time it gets back to a city, then steps down again. But step-up transformers live a lot in power distribution for the electrical company. And again, the small world of small electronics as well. So let's walk through what's going on in a step-up transformer. So first note on a step-up transformer is less windings on primary side. Whoops. And this one's going to have more windings. I didn't write it here, but primary, secondary. All right, so that's the first thing, is less windings here, way more windings on that side. All right, way more windings on the secondary side than the primary side. All right, couple folks writing, pencils down. All right, good. So this is how we get the increase in voltage. All right, the increase in voltage happens because I have more windings on the secondary side than I do on the primary side. So what does that mean? It means that I'm going to have lower voltage. This will have low voltage. Sorry, I'm going to slide this up because I'm going to need the bottom space down here. This will have high voltage. And now, important part as well, that you understand the other side of this. All right, the Ohm's law principle, which is the current. The current lives here also. This one's going to have high current. And this one's going to have low current. Voltage goes up, amperage goes down. And that's the important part, because this is the part that the fuses and breakers deal with. All right, just to kind of go back to the code book for a second. I need to know, if I'm connecting a step-up transformer, that I'm going to have higher amperage to deal with on the primary side than on the secondary side. This unfolds in a few ways. One, this means I'm going to need a larger fuse on this side. It also means that my wires need to be bigger on this side than the secondary side. So all of this is going to have an effect for us. I can lower this down a little. There we go. All right, if good so far, then the opposite, but we'll write it down because it's not just easy to go. The opposite for the step-down transformer. And again, this one is the one I meant to say was more common, although I had it first as a step-up. The step-down transformer. All right, we'll block this out again. We'll put primary side here. We'll put secondary side over here. And now the opposite of everything we just put over here, right? This one has less windings, but now, flip of the coin. This one's going to have more windings. And this one has less windings. All right, I'll simplify the notes here if you want to write it all out like the other one. This one has now the high voltage. This side has the low voltage. And high, this one has the low amperage or current. And high. All right, so opposite. Doesn't matter what voltage is now, but now you have to understand that as well. Since I have low amperage, this is going to have smaller breaker on the primary side. One of the things you see a lot in power distribution transformers, one of the transformers we run into a lot in the field, power distribution ones. And you'll notice they have a smaller breaker on the primary side, bigger breaker on the secondary side. All right, letting any notes that are being written down grab. All right, and last but not least, we'll start to wind this down today. This first introduction to it is the connections. And this is now going to follow us into the labs as well. All right, they're going to follow us into the labs as well, which is our connection points for the primary side and the secondary side are going to be H1 and X1 and X2 if this is a step down. All right, so the way we want to write that out is step down transformer, primary side, H1, H2, secondary side, X1 and X2. For the step up transformer, this is reversed, so I'll just write it down below for it. All right, for step up, then primary side is X1. Technically, it doesn't matter which, you put it. They're just got to be opposite of each other. So now H2, H1. This could be reversed. Doesn't matter which one I put where. Just as long as you reverse them. All right, so you'll notice like that, and you'll notice like that. All right, the ones are opposite of each other. And this really has nothing other than to indicate opposite polarity. So it does not really mean anything. So again, important things so far to understand. Step-down transformers versus step-up transformer. Which one has the high voltage on the primary side? Which one has the low voltage on the secondary side? And vice versa. And then same thing as far as the connections go. So if I give you an image and I say primary side and I show you this one here, for example, you should be able to tell me this is a step-down transformer. And if we see this connection, should be able to let me know this is a step-up transformer. All right, going back over. All right, I'm going to pause the